Okay, so we will today begin our last problem, which is the torsion of a non-circular cylinder. So it is sort of, let me say, appropriate to put this problem to the end of the lecture, end of the course, for several reasons. Now, first of all, the first problem that we solved was the torsion of a cylinder, but that one had a circular cross-section. So presently, it's not going to be circular. It's going to be some other solid shape, like an ellipse or a square or a equilateral triangle. This one, eventually, it's going to be a case study that I will consider next time, and these two you will consider in the homework. So that's one reason. Another reason, or there are several other reasons, some minor reasons. For instance, there are some mathematical tools that, of course, you're familiar with, but we never really needed them before, so I didn't even discuss them in the mathematical preliminaries. A good example is the Divergence Theorem and its derivatives that we're going to use again and again in order to attack this problem. So in a sense, I save this problem to the end because these are special tools that are only needed in this problem. I'll introduce the tools as we need them. Also, from a mechanical aspect, there is the concept of traction. We talked about what traction-free means, but I didn't really rigorously introduce what the concept of a traction is. So in this lecture as well, I'm not going to be very rigorous, but I will at least go a few steps further and tell what the traction is in its relation to stress, so that we can go ahead again, solve this problem. And finally, this problem, it's appropriate to save it towards the end because it can be solved both in a displacement and a stress-based approach. And now, by this time, I think we appreciate the challenges and the advantages of both approaches. So this is one problem. Of course, there were other problems that we considered where we could have done something similar. But in this problem, both the displacement and the stress-based approach are in settings that are actually not standard. In other words, they will deviate from the previous displacement and stress-based settings, and therefore also it's nice to consider it separately. So overall, this is a problem let's say, unique in itself, but the major ideas are borrowed from what we have done throughout the semester. Okay? So now, that's the geometry of the problem. So the coordinates, the axial coordinate is x3. X1, and out of plane is x2. No body force, no acceleration, length is L. So it's a prismatic bar. So the cross-section, however, is not a circular cross-section. So what I'm depicting here is, let's say, if you want the front view, or for that matter, the view at any cross-section. I'm assuming that the cross-section does not change. The cross-sectional area I will denote with S. So when I have an integral over S, it's over the cross-section. Any cross-section, if you like, throughout the cylinder. The boundary of the cross-section, in this case, it's a one-dimensional curved geometry, right? It's del S, okay? And moreover, I have to eventually, I will need this, I will introduce what is called the arc length parameterization of the boundary. And what the arc length means is simply I put a special coordinate around the boundary of this domain. And let's say this coordinate is called S, and it starts here. It takes a value 0. And as it increases, and by the time I come back to this point, the value of S becomes the physical length of the boundary. Okay, so S, therefore, is called the physical length of the arc that we are traversing. Okay, so that's the arc length parameterization. And finally, I will introduce the normal to this boundary del S. I will call it M, and it is outward, and it's a unit normal. Okay, so in this picture, M would be pointing at any point, let's say, towards us or above us or whatever, but always along the x1 and x2 direction. Okay, so it's always in the plane, let me say, of the cross-section. All right, that's the setup. Okay. Now, there is the origin. It turns out that really the choice of the origin in this problem solution is not really so important. It does have a few consequences, however. Now, if it were a circle, of course, we would pick it, let's say, or an ellipse, we would pick it to be right in the middle, in the square right in the middle. It's sort of natural, and that, what we call the middle in those cases, is the centroid. So in the case of equilateral triangle, again, you could pick it to be the centroid. So in general, I'm going to assume that this choice of the origin in the x1, x2 plane coincides with the centroid of the cross-section, and that will allow me to, let's say, more cleanly relate to results that we know from ME 231, our first mechanics course. Okay, but that's my choice. It's not absolutely necessary. All right, so the boundary condition, on the other hand, by the way, it's a torque. As we did for the circular cylinder case, it could be a torque, or it could be the absolute twist of the end where we're applying this boundary condition. And that twist is through an angle beta. Now, of course, as we also discussed in that problem, what eventually goes into the solution is not beta itself, but often the twist per unit length, which we called alpha when we were discussing the torsion problem, the very first problem that we attacked. Okay? So eventually, this parameter alpha I will also make use of in this problem. Okay? All right, so that's the setup of the problem. And now let us go ahead and attack it. And as I told you, it admits a displacement as well as a stress-based approach. So now I'm going to start with the first one, which is the displacement-based solution. So that's part one. Part two will be stress-based solution, and part three will be a case study of the elliptical cross-section. All right, so now let's proceed this way. So first, in the displacement-based approach, remember what we do always, whether it's displacement-based or stress-based, first we have to take this problem and propose a problem-tailored form of the solution, in this case for the displacement. Now, the problem does not really have any obvious symmetry, so I'm going to stick to the Cartesian coordinate system, but still, if I retain all the three coordinate dependence for all the three displacement components, then it's going to be a super complicated problem. I cannot hope to solve that one. So I have to propose a problem-tailored form. And here we recall another giant in the field. We're going to make use of the Semmenon theory. We mentioned his name several times already, and always associated with end effects, but essentially he was a person who gave a lot and essentially established parts of, let's say, elasticity theory in terms of presentation, in terms of notation, etc., I suppose. So, and he was the first person who really attacked this torsion problem rigorously and proposed a solution. So we're borrowing his idea here. And now first, to attack this problem, which is somewhat relevant to the classical problem with a circular cross-section, but it's not a circular one, so it's different. Let's recall first what the circular cross-section solution looks like. Now, in the circular cross-section solution, we have the cross-section only. Let me skip part one for a while. I'll just write cross-sections projection, and then I'll continue that in a short while. Let me go to part two. The cross-sections rotation, right? Okay, so we have a cylinder, we torque it, and every cross-section remains as a circle, and it only rotates. That's what our solution told us. And this cross-section rotation has to be small, right? Because we're looking at the small deformation theory, okay? And eventually it is described by, right? So the rotation of the cross-section at position x3 is simply equal to the twist per unit length multiplied by the axial position. So if I'm at the support, it doesn't rotate. And if I'm at the very end, the rotation is alpha times L, which by the boundary condition is beta. Okay? So that was pretty much what we essentially, this part is our observation. We did not assume this when we were solving the cylindrical, the circular cross-section problem, the torsion problem. We proceeded with a separation of variables. We did make a few simplifications there as well, but essentially this was the observation from the solution itself. So I'm going to still explain what the first aspect is, first observation is, but let me at this stage remind you what the solution for the circular cross-section was. Okay. So we have, so it's the circular one. We have done this in class. You have considered it partially in the homework as well, in one of the homeworks. And now I'm going to throw in here a few words that presently do not make sense, but I will explain how they relate to our understanding of the present problem. So I'm going to say the circular cross-section applies to the in-plane deformation. That part I will explain, but now let me remind you what the circular solution is. So there is a U1, right, and there is a U2. And essentially, the solution we had derived was in terms of the cylindrical coordinate system there. And we had found out that the angular displacement is alpha r. In the cylindrical coordinate system, the axial direction was z, right? So at z equals 0, no rotation. And then the angular displacement is proportional to the distance from the axis of the cylinder and proportional to the twist per unit length. So if we transfer that solution to the Cartesian coordinate system, we find that. Okay? So alpha remains, x3 remains, and r transfers to minus x2 and x1. Okay? Okay. So now, that is the cylindrical solution, sorry, the circular cross-section solution, and we do not now have a circular cross-section. So I brought the sponge that you will recall from ME 231, and we're going to do this small experiment now. At that time, perhaps it did not, we showed you that at that time as well, this tiny experiment, but now it will make a little bit more sense. So, we're going to torsion this, right? So if it were circular, the cross-section, we have these lines that are taken along the length. And when I torque it, the cross-sections only rotate. They don't distort in a way. It remains as a cylinder. Okay? But in the present case, those lines get distorted. Okay? So therefore, now first of all, this solution by itself obviously cannot apply, because there is a displacement in the axial direction, which you see from the displacement of the black vertical lines, right? Okay. So now, however, Saint-Venant proposes the following, or proposed the following at the time. So if you look at the cross-section from the front, and as you rotate this cross-section, okay, yes, a lot of things happen when you look from the side. But when you look from the front, what he proposes that, well, maybe the cross-section not only rotates, perhaps it distorts a little bit, but to a very good approximation within the limits of linear elasticity, so small deformation, he proposed that the cross-section only rotates still. So if you look from the side, there is an out-of-plane deformation, right, of the cross-section, depicted or indicated by the deformation of these black lines. But if you look from the front, and if you don't see the third dimension, you still see this rectangle only rotating, just like the cross-section of a circular cylinder. Okay? So Semmenon proposed that this observation is borrowed, and hence the in-plane deformation is sort of borrowed from our earlier solution, but you have to say that it applies only to the cross-section's projection onto the x1, x2 plane. Okay? All right? So that's the idea. So now that's what I had written there. So the circular cross-section solution applies, but only to the in-plane deformation, because obviously there is a out-of-plane deformation as well. And so the first item here says that the cross-section's projection onto the x1, x2 plane only rotates. Okay. So what does it mean that it only rotates? Let me borrow a different color to depict that. So for instance, if I had this rectangular or let's say square cross-section before deformation, I view from the front, and after deformation, we are proposing that it only rotates looking from the front. What could have happened is it could have also distorted. For instance, it could have, let's say, if it had gone under some sort of shear deformation, it could have not only rotated, but also could have distorted towards this trapezoid. But that's not what's happening. We're proposing that it's only rotating. So it's the dashed line that we are obtaining. Okay? So this is not happening. All right? So therefore, the in-plane deformation is already known, and in the Cartesian coordinate system, it's already described here. Now, the second piece of observation, again, comes from the observation of the distortion of these vertical lines. So now, the more I twist, the more there is a out-of-plane distortion. Okay? Now, we make two important observations. Now, first of all, when I do this twist, the way those black lines distort, right, they are more or less similar. If you look at that black line or that black line, okay, apart from some orientation influence, the distortion is more or less similar. In other words, the out-of-plane motion, it's the same for that black line and that black line. And moreover, the more I twist, the more that distortion is apparent. Okay? So we're going to put those observations together into a very simple proposal for the out-of-plane distortion. And this out-of-plane distortion has a particular name. It's called warping. Okay? And that is the special aspect of torsion of a non-circular cross-section. So the warping of a cross-section is, well, it's proportional to the amount of twist, but not the absolute twist. It cannot be, because the absolute twist rotation is proportional to the distance from the support. But what we are seeing here is that all lines more or less twist in the same way. So it's really the alpha itself only that matters. So it's the twist per unit length. That's what characterizes the deformation. And two, it is independent of, therefore, of x3. Okay? So these now we will put together. Okay? And propose that U3, the out-of-plane distortion, the warping, is described by alpha times some possibly complicated function of x1 and x2. Because the way those black lines on the sponge deform, they are not trivial. So it's going to be a complicated function, perhaps, but it's a function of x1 and x2 alone, and eventually there's a proportionality to the twist per unit length. Okay? And this function, C, is called the warping function. And it turns out that it's a geometric property of the cross-section. So every cross-section has its own warping function. And once you know that function, then you can go ahead and solve the problem for any given amount of torsion or twist, etc. Okay, so now that is our problem-tailored form. I know exactly how the displacement is. U1 and U2, they are trivial. I already know what they are. U3 has this complex C that now I need to go ahead and carefully look at. So now that we have the displacement, now I'm going to proceed step by step. Strain, stress, equilibrium, invoke boundary conditions, the usual procedure in the displacement-based approach. Okay? So let us do that over here. First, the strain, I'll start with the displacement gradients. So U1, 1, 0, U1, 2, minus alpha x3, U1, 3, minus alpha x2, 2, 1, alpha x3, 2, 2 is 0, 2, 3 is alpha x1. Okay, and then there is U3, 1, so alpha C, 1, alpha C, 2, U3, 3 is equal to 0. So that's the displacement gradient. So we can go ahead now calculate the strain. So it's 1/2 H plus H transpose. So skew symmetric terms, those are going to cancel. That's a 0. And then we have 1/2 let's say alpha over 2 C, 2, C, 1 minus x2. Right? And this one is symmetric. Diagonals are 0. So one more term comes over here. So it's alpha over 2 C, 2 plus x1. Okay. So let's also proceed with the stress. Lambda epsilon V identity plus 2 mu epsilon, but epsilon V, sum of the diagonal components is equal to 0. So stress is simply equal to 2 mu times epsilon. So it's symmetric 0, 0, 0. 0, 2 mu, so it's mu alpha C, 1 minus x2, mu alpha C, 2 plus x1. Okay, so equilibrium comes next. So the divergence, the stress field has to satisfy, in this case, divergence of stress equals 0, no body force, no acceleration. So the divergence of stress is going to be equal to one, 1, 1, 2, 2, 1, 3, 3. In Cartesian coordinates, it's easy to write the whole thing, so I'll go ahead and write the whole thing and then simplify. This has to be equal to 0. Now, some terms, of course, from the outset, they are equal to 0. I have no sigma 1, 1, no sigma 2, 2, no sigma 3, 3. Likewise, sigma 1, 2, and therefore 2, 1, they are 0. Okay. Now, moreover, sigma 1, 3, and 2, 3, they are functions of derivatives of psi and x1 and x2. And therefore, since psi depends only on x1 and x2 as well, there is no 3 dependence. So these terms die away. And therefore, if I look at these equalities, the first two are identically satisfied. I only have to worry about the very last one. Okay, that's what I need to enforce. So we must enforce sigma 3, 1 plus sigma 3, 2, 2 equals 0. And now if I look at here, right, 3, 1 or 1, 3. So derivative of this one dies. It's going to be mu alpha psi, 1, 1. And the second one is going to be mu alpha psi, 2, 2. So it is equal to mu alpha psi, 1, 1 plus psi, 2, 2. Okay? That's the left-hand side. And therefore, equilibrium is equivalent to saying that this term, which is essentially the Laplacian of psi, we now recognize. There is no third dependence, so we can throw away that third coordinate. So 1, 1, 2, 2 has to be equal to 0. So Laplacian of psi equals 0 for every, of course, point on S. Okay? So that for us is a partial differential equation. Okay? And let's call that equation star. I'm going to refer to it when the time comes. So our problem Taylor form for the displacement had this function, warping function psi, and equilibrium now imposes a constraint on the possible form of that warping function. Now that we have enforced equilibrium, the last thing that remains is the boundary conditions. So now we move on to boundary conditions. And what I'd like to do is I'd like to preserve this board up here still for a while. And let me move up here. OK, so now to discuss the boundary conditions, this is where I have to tell you a little bit more about traction. And I'm just going to draw that picture or something that looks like it once again. This is the cylinder. That's not a good one. Okay. So I guess we have to live with it for a while. So that is our cross-section. And we have the x1, x2, and x3 coordinates. So what I'll do now is first I'll take a small infinitesimal volume element, and one of the faces lies on the surface, and the rest goes inside the material. So I'm going to look at that infinitesimal volume element over here. And this is the face. The one on the right is the plane with normal x3. So it will have 3 stress components, sigma 3, 3, and then on the plane with 3 in the direction 1, sigma 3, 1, and this is sigma 3, 2. And that's the E3 direction. Okay. Now, on that plane, right, I have 3 components of the stress. So what I can do is, since I have 3 components in 3 different directions, I can think of these as being the components of a vector. And so this is the 3rd component, 1 component, 2 component, and that vector, let's call, okay, I'm just roughly depicting as such, and let me call it T. And it's a vector, the components of which are the components of the stress on the plane with normal 3. So I'm going to call it presently T3. I could have constructed a vector on the top surface. It would be a T1. Here it would have been a T2, etc. Okay? So that's a vector T. And now I also notice, sorry, if I take the stress matrix and multiply it with vector E3, so this is 3 by 3, okay, many components are 0, but in general 3 by 3, and this one is 0, 0, 1. And what I obtain is eventually these multiply out. Eventually I will obtain sigma 3, 1, sigma 3, 2, and sigma 3, 3. And that is nothing else than the components of this vector T3 that I have constructed. And now this vector we will call the traction, okay? Stress times some unit direction. And it's the, in particular, traction on plane with normal E3, okay? So this is the first time we are seeing the traction vector, a traction vector. Okay. Now, this idea where you take the stress multiplied with E3, you get a vector that has to do with somehow the components of the stress on that plane, can be generalized. In particular, when you take this differential element, I took it on the surface, so that we can easily see what happens. You don't have to take it in the surface. You can take it to be anywhere. And moreover, its orientation does not really need to align with the coordinate directions. It can be any arbitrary direction. When the direction is arbitrary, the normal to the surface will now be not necessarily E3, but any direction. And that could be, let's say, direction n for a arbitrary unit vector. So in general, if you would like to calculate the traction, not on the plane with normal 3, but on any plane with normal n, that's how you calculate the traction. Okay. I'm not being rigorous. I mean, it's not wrong, but we could have been more careful in the construction of this concept and its demonstration. But really, I have to go through all of this for a very simple reason. Now, I want to look at a very particular traction. I'm not picking any exponent to have a special notation. Again, it's a traction on a plane with normal, but this time m. Now, if we go back to our previous picture, or I can depict it here, m was on a cross-section, the outward unit normal that lies within the plane of the cross-section. So it's a unit normal pointing outwards from the cross-section, and it has no x3 component. Okay? So now I'm trying to calculate the traction on the plane with normal m. And that will have essentially to do with the components of the stress on that surface. And there will be 3 components. Okay? What are those components? How would you describe the boundary condition on the surface of the cylinder? Verbally, we've done this before. So on the right side, we impose a torque or a twist. On the left side, we hold it fixed. What do we do on the lateral surface? How do you describe that boundary condition? No, just think about any problem where we had similar scenario. did have similar, for instance, in the cantilevered beam as well. Okay, think of it as a beam. I apply a bending moment at the right hand or a shear force. What is the boundary condition on the top and bottom surfaces? Am I doing anything there? So what did we call it? Traction free. So what is the traction going to be? 0. Okay, I'm not doing anything. So now it's a little bit more clear. Traction free means that all components of the stress has to be equal to 0. So because now I'm going to say del S. Del S denotes the boundary of any cross-section, but that cross-section could be taken anywhere along the axis of the cylinder, and therefore del S anywhere in general indicates the surface of the cylinder, and it's traction free. So now that piece of information is essentially why we had to just quickly introduce the concept of a traction over here. Now I'd like to calculate the traction, but for that now, right, I know what the stress looks like. I've just calculated it before invoking equilibrium. Now to impose a traction or check whether I have traction-free boundary conditions, I need to calculate the traction, and for that I need to know the normal to the boundary. And so that's one additional piece of information that now I need to construct for an arbitrary cross-section. And I will do that, I think, over here. So let me draw the cross-section first. Okay, every time you'll notice I'm drawing a different cross-section, but it's all right. That's the boundary del S. Domain is S. I introduced, remember, a arc length parameterization, small s, okay, where it starts really doesn't matter so much, but it is counterclockwise. I'm careful about that. And out of plane direction is the x3 direction. And the normal that I'm trying to characterize in order to calculate eventually what the traction is, it's m here. And I will introduce yet another vector which is not normal, but tangential to the boundary. And I'm going to call it a vector tau. And this eventually will also be a unit vector. It's the unit tangent vector, and it is tangential in the direction of counterclockwise rotation. Okay, so now I'm going to do something simple. So for instance, what I can do is I can draw the in-plane position, right? Let's call it x, okay? Position of any point on the boundary. Let's say this is at a particular value of s. I don't know what that value is. And then I will go ahead and evaluate the position vector at some other value of s at a distance delta s from my first choice. Okay? And now I can calculate x s plus delta s minus xs. Okay? And this is the first vector. This is the second vector. And now when I subtract one from the other, it's this vector, right? Now what I will do is, or what you can notice is that as delta s goes to 0, this point is going to approach my first choice, and therefore this green vector is going to be more and more almost tangent, in fact, to the boundary. Okay? So it is natural for me to take the limit, therefore, of delta s going to 0. Okay? And the result is going to be simply dx ds, right? because every value of s gives me a unique position on the boundary. So on the boundary, if you like x is a function of s alone, and therefore I can take this derivative and evaluate the outcome, which is equal to tau. It's a unit vector. Okay. All right, so that's good. And therefore, the components of tau is dx1 ds, dx2 ds, and 0. Now, once I know what the tangent vector is, now I have a look at this picture over here. The outward direction is x3, and therefore unit vector is e3. If I take the cross product of tau with e3, I will get this vector m that I'm looking for. So m is equal to tau cross e3. Okay? So if you carry out the cross product, then you will find that m has components dx2 ds minus dx1 ds and 0. Okay? And now that's what I needed. And so now I can go ahead and really do what I wanted to do and look at the value of traction on the plane with normal m. So that traction vector presently, eventually, will live here. Okay? This is the traction vector that I'm looking at. And it's supposed to be 0 because that's my boundary condition. It's a traction-free boundary condition on the surface of the cylinder. So the stress, let me write it again because it's now on a different board. So I'm going to write it's symmetric. I'm going to keep the 3,1 and 3,2 components for convenience. So this one is psi comma 1 minus x2. This one is psi comma 2 plus x1. Okay, it's symmetric. And tau is equal to, m is equal to dx2 ds, dx1 ds minus 0. And I'm sorry that these vector components got entangled here. Let me squeeze the result over here. It's supposed to be 0, right? By the traction-free boundary condition. Now, these components are 0. This one is not, but the normal component is 0. So the first one is identically satisfied. The second one is identically satisfied. The last one is something, it turns out, that I have to be careful about or essentially enforce. And that last one is and I will write that in blue. So it's mu alpha appears in both components. I'm going to skip that and directly write psi comma 1 minus x2 dx2 ds. And then minus psi comma 2 plus x1 dx1 ds equals 0 for every x1, x2 on del S. So our warping function cannot be arbitrary. It has to satisfy two equations. The first equation had to do with equilibrium. It essentially boils down to saying that the Laplacian of psi, the warping function, has to be equal to 0. That's what I called star. And now there's an additional requirement. The boundary conditions are such that the lateral surfaces are traction-free, and that imposes an additional restriction on the form of the warping function. And it is this requirement. So these two requirements together will enable us to determine what the warping function is, okay? And you see that, right? Overall, so far, the basic steps of the solution procedure are pretty much the same as before. Problem-tailored form for displacement, strain, stress, equilibrium, boundary conditions, but eventually the implications or the form of the implications are non-standard with respect to the previous problems, okay? So now we're in good shape. That's essentially the hard part, okay? So we have actually the two major equations that we needed to have. But that's not all, okay? So now that we have the major things, let's get out minor things out of the way. We took care of the boundary conditions on the lateral surfaces. Now, the boundary condition here, I will postpone it. It's not a big deal, really, because it will be eventually coming in through our solution as an end effect. So when I do a comparison with the numerical solution, now remember, there's a warping, which this says that every cross-section will have also a displacement in the x3 direction. When I fix everything on this end, it cannot possibly get displaced in the x3 direction, and therefore the cross-section cannot warp at x3 equals 0. But that's going to be an end effect. It's going to exponentially decay the end effect towards the warped solution, okay? So this part I'm not going to worry about. But at this part, I must enforce static equivalence. In other words, the stress distribution that my problem-tailored form is implying should be such that here it's statically equivalent to only a torque. F1, F2, F3, they need to be 0. And the moment about the 1 and 2 axes have to be equal to 0. Only the moment about the third axis, which is equal to the torque, is not vanishing, okay? Now, I have to check how that is happening. And that's the last piece of critical information that we need to make sure that is satisfied, because otherwise the proposal, our proposal, tailored problem form, might have problems. Okay, it turns out it doesn't, but we have to verify it anyway. So let me move over here. Now, this part is where I have to just shortly remind you pragmatically about the divergence theorem, or really divergence theorem in disguise, if you like. So let me do one part, and then the rest follows in a similar fashion. So we must enforce, that's what we're trying to do, static equivalence. At x3 equals L. Now, if you like, have a look here for a second, and then you can go ahead and write. I'm going to work on that term, okay? And I'm going to write it in a slightly different manner here. So star is equivalent to, right? So I'm going to write this thing as the dot product of two vectors. The vector, the first vector, will have components c, 1 minus x2. And the second one has c, 2 plus x1. There is a third component, if you like, but I don't really need it because the whole thing can be described in a two-dimensional setting. So dx2 ds is the component of the second vector, and minus dx1 ds is the second component, and that has to be equal to 0, right? So when I take the dot product, remember, multiply the components, sum them up, you get that equality. Now, when you look at the right-hand side of the dot product, it's equal to the outward unit normal. It has a 0 in the third component, but I don't really need it, so I'm throwing it away. Now, this component I'm going to call, or this, I'm going to call the components of a vector v, okay? Now, this vector v is not anything that is very foreign to us at all. In fact, remember how that solution came about, a double star equation. So I'm going to pull down this board for a second. I think we see everything together. So psi comma 1 minus x2, psi comma 2 plus x1. So the first one is like sigma 3, 1, and the second one sigma 3, 2, except for a factor of mu alpha. Okay? So let me remind you that over here. Sigma 3, 1 over mu alpha, and that one is sigma 3, 2 over mu alpha. Good. Okay. So therefore, here we have v dot m equals 0. Okay. That is equivalent to the traction-free boundary condition. Now, moreover, let's observe also the following, because we are going to need it. Now, if I evaluate the divergence of the vector v, and that is v1 comma 1 plus v2 comma 2, and now if I look at the form of the stress, 1 comma 1, 2 comma 2, x2s and x1s, they don't contribute, so it's going to be psi comma 1, 1 plus psi comma 2, 2. Okay? And that is equal to the Laplacian of psi, and it's equal to 0 if equilibrium equation is satisfied. And I had called that equation star. Okay? That's equivalent to saying Laplacian of psi is equal to 0. So divergence of v is equal to 0 if equilibrium is satisfied. I keep that in mind. Right? Now I proceed with the a little bit tricky part. Okay? So now, I'm going to assume that double star, which corresponds to the traction-free boundary condition, which is now reformulated as such, is satisfied. Okay, so v dot m is always equal to 0. Now, if it is satisfied, then right, v dot m is equal to 0 everywhere on the boundary. Okay? So if I go ahead and take an integral of that quantity around the boundary, right, it's also equal to 0. If I throw in anything here, it doesn't even need to be a constant. It will also be equal to 0 because v dot m is equal to 0 everywhere on the boundary. Now, I'm going to throw in something special. I'm going to throw in x1. Okay? Okay? Now, therefore, this is an equality. It's 0 satisfied. And this is now a new vector, x1v. And now what I see is an integral on the boundary of a vector dotted with the outward unit normal, which tells me to employ the divergence theorem. Now, I will call every time that such an equality appears, I'm going to call it the divergence theorem. Sometimes it is the divergence theorem. Sometimes in a more general setting, when you're converting from a boundary integral to a cross-section integral, it has different names like Gauss, Green, or Gauss-Riemann, etc. So eventually, I'm just going to say divergence theorem. You should think when I say divergence theorem, it's related somehow to the divergence theorem. So the divergence theorem says that essentially integral on the boundary becomes an integral over the domain of the divergence of the vector that appears here, which is divergence of x1, b. Okay? So here I imposed it. Okay, so that's good. Let me work out what this derivative is. It's the components of the vector, comma 1, plus the second component of the vector, comma 2. Okay, so x1 v1 comma 1, x1 v2 comma 2. Now, if you calculate the derivatives, then x1, comma 1 leaves a v1. And then x1, v1, comma 1, and x1, v2, comma 2 will come here. And therefore, x1, v1, comma 1 plus v2, comma 2 is going to appear. And the term in parentheses is nothing but the divergence of v. And the divergence of v is equal to 0 by the requirement of equilibrium. Okay? So this term died away, and I'm only left with v1. Now, v1, on the other hand, I reminded you here, it's sigma 3,1 over mu alpha. And therefore, this whole integral, which has to be equal to 0, we have condensed it to a domain integral, which has 1 over mu alpha sigma 3,1 dA. And integral over the cross-section of the stress distribution in the one direction is nothing but the force in the one direction. And therefore, what we have found out that F1 has to be equal to 0. Okay? So I needed to enforce static equivalence, so F1 had to be 0. But it turns out I don't need to do anything special. If traction-free boundary condition is satisfied, and eventually if equilibrium is satisfied, then F1 is identically 0. Now, you can show that similarly. Instead of starting with this special integral, you can start with a special choice of an arbitrary function as x2. V dot m is 0 everywhere on the boundary. And then, if you proceed with exactly the same steps, you will end up with 1 over mu alpha integral sigma 3,2 dA, integral over the cross-section, equals 0, right? And this here is nothing but the force in the second direction, and therefore F2 will also be identically 0. So we just have to keep in mind that these results require both equilibrium and traction-free boundary conditions are satisfied. As long as they are, then I don't need to worry about them. Okay? All right. So how about F3? Well, F3 is simply integral over the domain of sigma 3,3, but sigma 3,3 is already 0, so it's identically satisfied. Okay, that's easy. And now we move on to the moments. And we have 3 moments. Unfortunately, I just erased the diagram. Okay, here's a quick sketch. So we have M1, and we have M2, and eventually M3. Now, M1, it's a moment in the one direction. So it has to do with this sigma 3,3 component. In-plane components do not cause a moment either in M1 or M2 direction. So it's going to be sigma 3,3 dA. And for it to be in the M1 direction, sigma 3,3 causes a moment about x1 if you move away from x2 equals 0, and therefore it's going to be an x2. Okay? And if you want to calculate the moment about the x2 direction, it's again sigma 3,3. If you are in the positive x1 direction, the moment, however, it's caused in the reverse direction because sigma 3,3 is positive, sigma x1 is positive, it the direction of moment is minus x2. And therefore, I have to put a minus sign here, x1. But after you think about all that, you notice that sigma 3,3 is equal to 0. And therefore, moment about 1 and 2 directions, they are identically 0. You don't have to worry about them. What you do have to worry about is the moment in the third direction, which is the torque that we are imposing, or the torque that you are measuring if what you are imposing is the end twist. And so in that case, in a similar fashion, using the in-plane components, you can find that the torque is equal to x1 sigma 3,2 minus x2 sigma 3,1 dA. Now, we've indicated the components of the stress several times. Let me plug them here. So we have here x1. I'll take mu alpha outside because it appears in the components. So psi comma 2 plus x1. And then minus x2, psi comma 1 minus x2. So I'm just going to put together terms, x1 squared plus x2 squared. Plus x1, psi comma 2 minus x2, psi comma 1. Okay, so now we will give this integral a name that will be, well, first a symbol, not a j, but a j tilde, right? So now, why j tilde? Because this term here, x1 squared plus x2 squared, is the radial distance squared. And remember that the polar moment of inertia is integral over the area r squared dA. Okay? So what we have is almost a polar moment of inertia, but there are additional contributions that have to do with the warping of the cross-section. And therefore, it's not a j, but it is j tilde. And we're going to call this simply the torsion constant. And as in the classical use of j, and I will just remind you in a few seconds, this has to do with the torsional rigidity of the cross-section. So the higher it is, the more rigid the cross-section is with respect to torquing. And as you notice, since psi is a function of the, or it's a property, geometric property of the cross-section, this whole thing, just like the polar moment of inertia, it's a property of the cross-section. And now we can put all of this together, right? And what we see is that alpha is equal to T over mu j tilde. Okay, so this is the twist per unit length. So now remember the absolute rotation at x3 equals L. We called it beta, and it's equal to alpha L, okay? And because theta is alpha times x3, right? So alpha L is equal to TL over mu j tilde, right? So which now is perhaps an equation that you will remember, right? There, twist and twist is TL over the shear modulus times j is what we had for a circular cylinder. But now it's not j, it's not the polar moment of inertia, but something else, j tilde, which is very closely related to the polar moment of inertia. But if the cross-section is not circular, there is a warping contribution. And we will see eventually how that contribution comes into play. So this equation will allow you to find the end twist, or the twist per unit length, if the torque is prescribed, or if you are prescribing the twist per unit length, then through this equation, you can find what the torque is, all right? So we are in a good shape. Actually, what we've done now is we've completed the displacement-based solution approach. So next time, I'm going to proceed with the stress-based solution approach. And just like for the present case, it's going to have its unique features that were not present in previous stress-based solution approaches. And once we complete those two, I'm going to proceed with just actually one example on the elliptical cross-section and hopefully a numerical comparison as well. Okay, so thank you.